A density column is actually a fun and simple experiment that you can try at home. So here's all the materials that you're going to need for this particular version. There's lots of different ways to make a density column, but I really like this one, and hopefully you'll like it too. So here's all what you'll need. Water, which I have in this graduated cylinder. Vegetable oil, I'm using pure canola oil, but I don't think it really matters what you use. Isopropyl alcohol, which is also known as rubbing alcohol, but make sure it says isopropyl on it. Some of them are different types. 91% is the best. If you can only find 70, that will also work. You'll just have to use a little bit more alcohol. Some salt, food coloring, and an empty bottle or jar with a lid. I'm going to use a small vial because rubbing alcohol is kind of a precious commodity nowadays, so I'm going to try to limit the amount that I use. To make the column, we just add equal parts of all three liquids to the vial. It doesn't have to be exact. I'm going to use this graduated cylinder just because I have it, but you don't need to be that exact at all if you don't want to. I'm going to add 10 milliliters of each of the liquids. So we'll start with water. Next, I'll do the canola oil. And you see the water and the oil don't mix, so we get two nice distinct layers. And then finally 10 milliliters of our rubbing alcohol, the 91% isopropanol. Had a little bit of excess oil in the cylinder, so you see that's kind of dripping in now. And there we go. Now you have a 3-layer density column. Now to see things a little better, I think we should add some food coloring to it. So I've got blue food coloring. You can use whatever color you want. And since my vial is really small, I'm just going to add 1 drop. And now I want to mix it around to get the color all through it. So I'll put the cap back on and go ahead and shake it. Okay, and then we just wait for that to settle out. All right, I've let it sit for about 20 minutes and everything is settled out, but hold on a second. We've only got 2 layers now. So this is definitely the oil layer. You see it's still yellow. There should be a blue layer above it, but there's not anymore. It's all below it. So what do you think that would be? Well, it turns out that the top and bottom layers, the alcohol and the water, can actually mix together. The only reason that they were in separate layers is because the oil was separating them. So when we shook the vial, we disturbed the layering, and the top and the bottom layers got combined into one. So that's unfortunate, but it turns out that we can actually use a really cool chemistry trick to separate those 2 layers back out, and it's called salting out. And this is, as you might have guessed, where the salt comes in. The idea here is to saturate the water with salt so that no more can dissolve. And if you're an especially clever chemist, you can calculate how much salt you should need to saturate the amount of water that you have. And I went ahead and did that, and this is what I think is the amount that I should need. But if you didn't measure your liquids exactly, or you're not sure how to do this calculation, no big deal at all. Just add a whole bunch of salt. You can't add too much. So we'll take the cap off. Pour in my salt. Hopefully I don't overflow my vial. Okay, that was a close one. And I'll put the cap back on, and now we just want to dissolve all of this salt into the water. And since I've got a nice vial with a cap on it, I'll just shake it around again until everything is dissolved. So I've shaken this for a couple of minutes, and there's a little bit of salt left on the bottom still, but I think that's about as well as we're going to dissolve. So let me shake it up again, and you can watch the layers separate. And check it out, we're back to 3 layers again. It's interesting too, it took way less time to separate out than it did before. I wonder why that is. So I know this is a video about density, but this is a good excuse to take a little detour into another area of chemistry and talk about polarity. Polarity is the separation of electric charge across a molecule, and the different polarities of these different liquids is why they're able to separate out again. So here's a diagram I drew to help explain the concept. Water is a very polar molecule because it's shaped like this, and electrons are attracted more towards the oxygen atom and away from these hydrogen atoms. So this means that this side with the oxygen is more negatively charged, and the other side with the hydrogens is more positively charged. That makes it polar, very polar. Isopropyl alcohol, which is our rubbing alcohol, is slightly polar because it has this kind of a charge separation. The electrons are drawn up to this OH group, so you get a negative charge on top and a positive charge in the middle, but this difference in charges is sort of shielded by these 2 groups on the sides, which don't have a charge. So it is polar, but it's kind of protected by these 2, so it's not as polar as water. Isopropanol has a bit less than half the polarity of water because of this. And oils, like our vegetable oil, are made of very long chains of carbon atoms that sort of look like this. So they're more or less symmetrical, and there really isn't anywhere that pulls electrons more than anywhere else. And that means that our oil is nonpolar. So when we add salt to our water and alcohol mixture, salt is NaCl, when it dissolves in water, it turns into ions, sodium ions and chloride ions. And so those are charged as well. So what it does is it increases the polarity of the water layer by adding more charges. And so that actually drives out the alcohol from being mixed in with the water because it's less polar. And so we get a new layer to separate back on top. Another thing that's interesting to notice is the color. You see how the water layer at the bottom is a bit darker than the alcohol layer at the top? And then the vegetable oil is not colored at all by the food coloring? That's also because of polarity. The food coloring is water soluble, which means it's also very polar, just like water is. And so the food coloring will mostly migrate to the water layer and stay there. Since our alcohol is slightly polar, it takes some of the food coloring up into it, and you get a bit lighter color there. And then since the oil there is non-polar, it doesn't accept any of the color, and it remains that light yellow. Anyways, back to the original topic here. The reason that these 3 layers form like this is because they have different densities. Water is the most dense, so it stays at the bottom. Oil is a bit less dense, so it floats on top of the water. And then the alcohol is the least dense of the 3, so it floats all the way on top of everything else. Now the coolest part about this version of a density column, and the part that I like a lot, is that you can keep on shaking it. Now that we've got our 3 layers set up, we can just shake it again and again and again, and they'll get all mixed together, but they will re-separate out back into the 3 layers every time. A lot of density columns, you're actually not supposed to shake them because it'll disturb the layering and then mix them together, just like what happened at the beginning, and they won't separate out again. But this one works even if you're clumsy and knock it over by accident. I also think it's super cool to watch these little bubbles as they rearrange themselves. So that concludes this video on density. I hope you learned something new and got to try some of it for yourself, and maybe ended up with a cool little density column to impress your friends with. See you next time.